So, what are benefits and open challenges for photovoltaic technology?
There is very small fraction of the solar power converted into energy. We do not need fossil fuels. We do not need radioactive stations. Just solar. But the question how to make it efficient, because actual solar panels actual solar panels are like 10% efficient, and there is a theoretical limit for about 35% efficient.
Really?
Oh yes. Yes, and there is an effort in scientific community to find principles and mitigate this losses into heat. Like radiation comes, and instead of electricity, just heats it up.
Let's overview traditional materials for solar cells and photovoltaic technology.
There is a famous scientist in Switzerland, Michael Gretzel, who told, let's take titanium dioxide, which is typical sunscreen from cosmetics, pour raspberry juice on it, and then connect it to electrodes. This also gives electricity, and it is doable at home. There are some little tricks, but it is doable by a high schooler. So cosmetics, titanium dioxide, here is the crystalline structure. Red is oxygen, the silverish is titanium. So it connects, each titanium connects to 6 oxygens, which is called octahedral, but it is slightly distorted. It's anodized. And this serves as it pulls electrons from whatever it has access to. And when one places organic dye, a little molecule, one hits it with light, and then when it is excited, then this greedy titanium dioxide pulls electron to there. And then one has another electron and separates charge and makes electricity. But this is degradable, and it will be quite ridiculous to make industrial plants based on raspberry juice. Today's solar cells are made of silicon, which have a diamond structure. If you see this way, you see perfect hexagonal. If you look from another angle, from this one, it's also like a honeycomb. And in order to create separation of charge, one dopes silicon with phosphorus, nitrogen, arsenicum, and then upon light hits it, positive charge goes to one side, negative to another, and then one puts a metal contacts and it goes to the bias. So not too bad, but one needs crystalline, perfect. If one melts and crystallizes, it may create some defect that will trap charge and prevent it from being efficient.
Let's look on recently discovered new materials, promising new materials for photovoltaic technology.
So during recent 5 years, this perovskite was found to be much more efficient than silicon. This one is perovskite. So the greenish is lead, which is toxic but very useful for this application. Yellowish is iodine or bromine or chlorine, and silverish is, for example, cesium. That could be. So I was telling it to my friend who is an artist who make portraits for living, and I told I'm sorry, I need to study these materials because they have lead. It is toxic and maybe not good. And for my whole life, I paint portraits with lead paints, and people are buying it. So what's the problem? Now, next thing. If on one angle, let's look only on the greenish things. You see, it looks like a cube. If you look on the yellowish things, they look like edges of this vertices, and silverish is like a feeling inside. Why it is so interesting and non-usual? Those in regular materials, the bonds are so-called covalent. They are very strong and well-defined. Here, those are ionic. So this lead, bromine, and cesium. Lead is positive, cesium is positive, bromine is negative. So like table salt in school, middle school, high school chemistry. So they're just connected by ionic bonds, and they're moving. So this cesium freely floating in this cavity,
What are unique properties? What is good about new materials for photovoltaic technology?
The dielectric constant, which is like 1 for vacuum, 80 for water, and 1000 for perovskite. So it's a highly dielectric material, semiconductor. And this is responsible for many of the properties. Is that electron and hole? What do we remember about them from like high school? One is positive, another negative. Yep. And positive and negative like each other, they attract. So even they're generated, they are connected. And they do not want to go to metal electrodes. They do not want to give us electricity. They thought, no, we are happy together. We will give you zero electricity. So one needs to break their connection. And in this material, in perovskite, this cesium cation inside, it's freely moving inside little cage. It is charged. And if there are like electrons and holes outside, this material will polarize and compensate electrostatic interaction of electron and hole to zero. So electrons and hole in perovskite do not interact anymore. And the perovskite is interfacing titanium dioxide and another material for collecting holes. So one hits with light, and then electron goes one material, hole another one.
What are benefits? What is the future expectation of photovoltaic technology?
So-called photo-induced charge transfer, which is key process for photovoltaics, for solving energy problem for the globe, because just little area in the Sahara Desert or in Arizona Desert, like 100 by 100 miles or a little bigger, if it is populated by 100% efficient solar cells, it will give all energy that whole globe needs.
All energy that whole globe needs.